All right, I'm gonna give a couple more minutes for you to finish. Some of you are here still discussing, so make sure you're getting the questions done, and then we'll go over them. Goes back. All right. Um, so our outcomes for today, we're going to be using the rules that we've discussed for the past two class meetings, um, and now we're going into using conversion factors to change from one unit to another. So the process is called dimensional analysis. In math, it might be called factor label method if you've ever went through that. It's really just a way of keeping track of units while you're doing some calculations. Again, this is more of a method of showing your work, not necessarily how you enter it in the calculator. However, you can do that just with some simple steps. All right. Going back to the metric units that I showed yesterday, I'll probably pull that slide back up again today. But remember, you're going to need to know pretty much from mega down to nano on that list. So make sure that you're kind of getting those, and we'll need to know the unit changes on it. Like I said, I'll pull that one up again when it's needed. And then we should be able to convert measurement from one metric unit to another, and then be able to convert from imperial or British to metric units. The conversion factors that we'll need to use as far as the imperial to metric, they're in that periodic table reference packet. If you ever need an extra copy of that or another copy of that, I always have copies. I'll always have copies up here, so you can just grab another one as you need it. So going through today's stuff. All right. So on the first one, it was just simple addition. So going across, what would our unrounded answer be? All right. Now, based on the rules for addition and subtraction, what am I gonna? How many decimals or sig figs am I? Or how many decimals am I gonna need? Just one, because this one only has one decimal place, so that means that my answer can only have one decimal place. So the correct answer would have been 22.3. All right. What's the unrounded answer for the second question? All right. And then when we look at this, how many decimal places can my answer have? One. So in this one, 16.6. Before I move off of these two, addition and subtraction, any questions? All right, remember that for addition and subtraction, your answer can only have as many decimal places as the one with the least, or not necessarily just decimal places, but your answer can only be written as the least precise part of the prompt. All right, so in both problems 1 and 2, you only had one decimal place in each of them. On some of the active from yesterday, you had one where your answer only went to the tens place. So your answer could only go to the tens, like have anything hundreds, thousands, all of that, but it could only go to the tens place. All right. For our multiplication division, remember the rule is it counts by the lowest amount of sig figs. So when we do 14.922 times 2, get 29.844. And then how many sig figs should my answer have? 2. Now, here's an issue. When I round this to 2 sig figs, how do I show that that 30 represents 2 sig figs and not 1? I can put a decimal right in behind it. I could write it in scientific notation as well. Scientific notation would be writing more than I need to in that case. All right, and the last one, 64.77 divided by 9.11. You get 7.0. Oh, no. All right, so 7.109769, and I need to round that to 3 sig figs. So what will that be? 7.11. All right, any questions on those? Again, none of these were combined problems. However, they do. You remember, if it's a combined problem, the answer is going to be based off the last rule that you followed. If your addition subtraction is the last thing you do, you're going to follow by the least precise measurement. If multiplication division is the last thing you do, then you'll follow by the total number of sig figs. All right, if you would, real quick, and I'm going to give some time to do this. I want you to go ahead and go to Google Classroom. In Google Classroom, I want you to click on the today's assignment thing. I'm going to show you some things in there. One of the things throughout the day yesterday, a couple of students asked for some extra practice stuff so they can see some of these different types of problems. So I did include this worksheet, and then I also included the key. So if you want to go through and practice some of the things and see if you come up with the same numbers I did and all of that, and then if you have questions, I can answer them in class. But what I would like for us to do right now is go ahead, click on this that says Sig Figs Practice right here. On here, I want you, when it pops up, it should pop up with a question eventually. There it is. There's 20 questions on this. I want you to go ahead and try this. After you get to the end, when it shows you results, if you could screenshot it and put it in this assignment, you can. There's even if you have to use your phone to take a picture of it and put it in there, you can do that. But I know you can screenshot on the Chromebooks. I just don't remember how. But that's something you're going to want to get used to doing anyway. I'll look it up in just a minute. But go ahead and go through this. It does have the rules on the side, so take a few minutes and work on those. Explain what I mean on that. So one of the things you can do whenever you're reviewing your stuff, if you click Show All Questions, it'll show all of them at once. The ones that I had an issue was like this one. It's my number 3, but they randomized the question, so it may not be your number 3. But where I'm reading this ruler, my first choice would have been this 5.65, because I would have said that it measures that my estimated digit is to the hundreds, because I know 5.5 for sure. So they were looking at this as, since it only measures to the 0.5, that you can only that anything not 0.5 is estimated. So I get where they got that. I just would have read it as 5.65. So be careful on those. I don't think on the test and all of that, it won't be that ambiguous. It'll be more straightforward, because there was another ruler one that had actually all the way to the tenths. That one you had to go one digit past. The other one that I felt like, again, was just ambiguous on it was this one with, well, the other one with the ruler on this one, but I had already figured it out that they were only asking you to measure to the tenths or estimating to the tenths. But this one with the graduated cylinder, again, it's that same situation where you have, it counts by ones and then it measures to 5/10. On this one, they wanted the correct answer of 8.0. I probably would have chosen 8.00 in this case. All right. So just kind of be aware that there is some little bit different perspectives on those and things like that. And just kind of deal with that. All right. Now, going back to our notes and going back through this, I'm going to try to include some of those practice things in here. Probably not during class all the time, but I will put some of those links. That the page that I was using is called Science Geek. They have a lot of like review games, but you just have to kind of go in there and dig to find them, and they're all HTML based, and that you can do that. Some of them are better than others. It just depends. All right, so one of the first things that we're going to look at today is distinguishing weight versus mass. Whenever we say that we're measuring something in grams, we're actually measuring mass. So all the scales that we use to measure in grams, they're calibrated to use a specific amount. So no matter where I take this digital scale, no matter what planet I take that digital scale to or anything like that, I'm going to calibrate it with this hunk of metal. This hunk of metal measures 200 grams. So when I put that on there, the scale will read 200 grams, and I'll calibrate it to that. So this piece of metal is not gravity dependent. If I'm saying that this piece of metal is 200 grams, no matter what the gravity is, it's going to be 200 grams. So mass, when we're measuring using a scale that is calibrated to a specific thing like this, that's going to be a mass. When it's a spring scale like you have in your bathroom, that measures weight because that's measuring how much gravity is pulling down on you. So the mass of an object is a measure of the quantity of matter within it. So if I have a mass scale, no matter where I go, if I use the same scale, it's going to give me the same number every time. If I'm measuring weight, my weight on Earth would be 6 times greater than my weight on the moon. Things like that. All right. So, and so weight is just simply a measure of gravity that pulls on it. So mass is a measure of quantity of matter. Weight is a measure of gravitational pull on that matter. So if you want to think of it like this, weight is more analogous to a force than mass. Mass is just the amount of material. So weight depends on gravity while mass does not. Now keep in mind, there are some scales that will measure in grams that end up taking a weight as well, because there's some spring scales that measure in grams. But if you're using a calibrated scale based off of a known standard, then it's always going to be a mass. All right, that one shouldn't be. All right, so give me a second. Give me a second to pull this up, and we'll do this. So pulling up that scale that we had yesterday, the one for unit conversions between metric prefixes. So one of the things that I want you to realize, so like if we're saying that our base unit, remember our base unit can be things like a meter, a liter, a second, things like that. So in this case, I'm saying I have 6.2 nanometers. So I have in M, and I'm trying to go to just regular meters. So on here, I'm going from here to the base. All right. Now, when I do these, I want you to pay attention to, so like in the past when you've done these, you might have done like, I know one method they teach in elementary school and middle school is that little stair method where you put them all on the stair. So like if this is your base, you would have milli, centi, deci, base, and then you would have deca, deca, hecto, and then kilo, right? And you would just count and move the decimal. That's fine between kilo and milli, but notice what happens to the size of the unit from like milli to micro. Notice it goes up by 3 orders of 10. And then this goes up by 3 orders of 10 as well. So that would represent 3 movements of the decimal place. And we can't just do that. So we have to find a way to, I'm going to show you a way that I kind of do this mathematically. I'll post a video from Melissa Barabel, but she does it a little bit differently than I do. So the thing that I try to do is I pick whichever unit is larger. All right. So in this case, meters is my larger unit, right? So whenever I'm doing this conversion, I'm trying to go from nanometers to meters. So I'm going to say 1 meter, and I want to find out how many nanometers that is. So the way that I do this is I look at these exponents. All right, and that's nano. Nano is 10 to the 9th. All right, so nano is 10 to the 9th, and base is 10 to the 0. So I'm just going to take the exponents, and I'm going to go 0 minus a negative 9. All right, so 10 to the negative 9, and 0 is what I'm comparing. If I do it this way, and I always put the larger one first, I should come out with a positive number in my answer. So what is 0 minus negative 9? 9. All right, so that means that a meter is 10 to the 9th. And I mean, it should kind of relatively make sense. A meter is 10 to the 9th bigger than a nanometer. So whenever we're looking at that, we got to divide by 10 to the 9th to get 2 meters. So do 6.2, divide it by 10 to the 9th. No, because I'm comparing it to 1. So I'm not going to use that. If you wanted to flip it the other way, you could have said 10 to the negative 9 over 1. But that's saying that you have 10 to the negative 9 meters to 1 nanometer. I do this. You'll probably like Miss Melissa Barabel's video better because she does it the way that you're trying to do it. I don't like using negative exponents. I eliminate the negative exponents, and I'll show you more. So when you do this, and 1 over 10 to the 9 is a negative number, 10 to the negative 9. It'd be just like multiplying by 10 to the negative 9. So when I do this in the calculator, I'm going to get 6.2 times 10 to the negative 9, or I'll get, if I did it in standard notation, it's at 8 zeros and then 62. A decimal point, 8 zeros, and then 62. There should be 9 places. All right. So I'll do this a couple more times just to kind of get you used to it. Now, here's the thing that I'm going to show you. So we've done milliliters to liters before. That's the one where you could just use the stair step. So if I'm starting here, I'm going to move 1, 2, 3. Or if I'm starting here, I'm going to move 1, 2, 3 spaces. So that means if I bring it back, I know that my answer is going to be 26.4 liters in that case. All right. But mathematically, I want to show you how it gets there based off of those exponents just to show you again. So again, I'm setting this up 26,400 milliliters. I'm going to put milliliters on the bottom because that's what I'm canceling. Liters on the top. Which of the two are the larger unit? Liters. So liters gets the 1. Now, I look up my things on there. So I have 0 minus negative 3, which gives me 3 places, right? So I'm dividing by 10 to the third. So if I take 26,400 divide by 10 to the third, what number do you get? Should be 26.4. All right. So there's nothing wrong with the way that you were taught to do it, where you just move in the decimal place. The problem is that it has a failure between here and here, and between here and here, because you're looking at 3 magnitudes of 10 higher. That's why I teach you to just subtract the exponents like I did. Take the larger exponent first, subtract the smaller exponent, and then it'll give you how many orders of 10 difference. Well, then do that for you. All right. So, so this one, we're going from kiloseconds to milliseconds. All right. So which unit is the smaller unit in this case? I mean, which unit is the larger unit in this second? The larger unit is kilo, the smaller is milli. So I'm going to say for every 1 kilosecond, I need to find out how many milliseconds. So again, milli is 10 to the negative 3. Kilo is 10 to the 6. So 6 minus negative 3. Oh, sorry, 10 to the third. Sorry. 3 minus negative 3 is 6, right? So I was answering my question while I was writing. It's 10 to the 6. So 892 times 10 to the 6th gives us what? All right, 892 million milliseconds, or we can write it as 8.92 times 10 to the 8th, because I had to move it to more places. All right, try to do E, see what you come up with. Remember, E is already in scientific notation, so if it helps you to write it in standard notation first, do that. check your answer. I get 5,600 when I do this. And the reason, so the way that I do it, the way that I approached it, mega is the larger unit. So I set it to 1. Deci is a -1. So mega is 10 to the 6. Deci is 10 to the -1. So I go 6 minus -1. That gives me 7. That's where that 7 came from. So I multiply this times 10 to the 7th. And that gives me that. You might... Yeah, I'm just setting it up to a ratio. So I'm establishing a conversion factor for each of these. That's why I'm showing you that method. I take the exponents. I take the larger exponent. Huh? Mega is 10 to the 6th. That's the exponent right there. Deci is 10 to the -1. And your base is always going to be, so these are always going to be decimeters, deciliters, deciseconds, hectometers, hectoliters, hectoseconds. So it's not those deci, centi, milli, micro, all of that are prefixes that go in front of a base unit. And so if I'm not going to the base first, then if I'm going to the base first every time, it's easy. I can just use the exponent there and multiply or divide by it. But if I'm not going to the base first, I can use those exponents that I'm given here and set it up, the larger minus the smaller, and then it'll do it. And if it is a negative exponent, it's going to be a minus the negative exponent, which gives you a positive number because you're covering a large distance. This way always should give you a positive answer if you do it this way. And then that way it always sets your exponent as positive. And the way you get the positive or negative is it ends up either on the top or the bottom. The unit that you're canceling is always on the bottom. We're going to see more of these, and I'll pull some of these up from active and things like that, and I'll pull up some more practice problems for this. So let's look. Let me do this. Because if I need to take more time on it, I'll take more time on it. All right. All right. So, again, let's just take one, I don't know, 342, all right. So if I want to do 342 millimeters, and I want to know how many megameters that is. So go ahead, try to see what you get, and then I'll post and I'll put up what I get in just a moment. It's not to the 11th, negative 11. It'd be to the negative 7.
7. I got 7, 3. You got 10 to the 7.
So there's 9 orders of difference, right? You got that. Okay. So if you're dividing by 10 to the 9th and you're already in 300, so move the decimal place. That's where you get the 7. Yeah. So you get decimal place 6 zeros, and then I know how you're getting 11 because I thought that when I did it just in my head, but then when I put it on paper, it made sense why it's 7. All right.
This is hard.
All right. So just showing you my process step by step. So the first thing I'm going to start with is my given, 342 millimeters. Since I'm in millimeters, I'm going to put millimeters down here because I want to be able to cancel and get rid of millimeters. That's the only reason why I'm showing it in fraction form. All right. Now, I know I'm going to megameters. Megameters is my larger unit, so I'm going to set it to 1. So I want to establish a conversion factor between millimeters and megameters. All right. So I'm going to look. Mega is 10 to the 6th. So I'm going to go 6. Minus milli is negative 3. So that means I get 9 powers of 10 difference. So that's 10 to the 9th is what I'm putting there. So all I'm saying is that for every 1 megameter, I have 10 to the 9th millimeters. I could write this in another way. I could say for every 10 to the negative 9 megameters, I have 1 millimeter. That says the same thing. Those are equivalent statements. If you flipped the equation that I did and did it the other way, you would get the other answer, right? If you did negative 3 minus 6, you're going to get negative 9. Should. I'm not worried about the answer just yet. I'm just trying to show you the process first. Let me get there. All right. So now I do 342 divided by 10 to the 9th. And that either gives me 0.000000342 megameters. This answer should make sense. Since we were in millimeters, which is a smaller unit, we went to a much larger unit. We're expecting a decimal number or a part of that. All right. The other way that you could have written this, 3.42 times 10 to the negative 7. All right. And just going back to yesterday, tying this into yesterday, the way that I get 10 to the negative 7 is I'm moving that decimal 1, 2, 3, 4, 5, 6, 7 places. All right. So because I'm already in the hundreds here. Yeah. I'm not processing what you're saying. There's 9 numbers in total. You're correlating two things that should not correlate. I added enough zeros to put it into that new unit. That's all I did. I divide it by 10 to the 9th. I took this number that's in the hundreds, divided by 10 to the 9th. All right. So let's look at a different one, maybe one that's, this is an actual conversion that you will probably end up doing in this class. All right. So one of the things that we deal with is light waves in this class. So light waves are usually measured in nanometers. All right. So all right. So if I have something that I burn and it produces a green or blue light, and we measure it with a spectrophotometer, and we get that the wavelength of light is 537 nanometers. Well, to calculate the energy, I need to know this in meters, because energy is related to speed of light. Speed of light is meters per second. I know that number. So I need to get this number to meters. So again, my first step is I'm going to take my given 537 nanometers. I want to get rid of my nanometers, and I want to go to meters. Meters is the larger unit. So I need to find out, because my brain just registered a 4. All right. One thing came out of my head, the other thing came out of my hand. All right. All right. So now I need to establish a conversion factor between nanometers and meters, right? So I'm going to look over here. Nano is 10 to the 9th. Meters is on base, so it's 10 to the 0. No, you have to memorize this. All right. So 0 minus -9 means that we are 9 orders of 10 difference. All right. So now, when I do this one's going to give you what you were trying to get earlier. So when I do 537, nope, I did it in my head wrong again. This one would be to the -7. So (5.37) times 10 to the -7. It's the other way that it flips. All right. So when we look at this, the method I'm trying to show you is one that you don't ever have to go to base unit. A lot of the videos that you'll watch will teach you to go to base first and then go to the next unit. This one we happen to be going to base. Again, the other way that I'm trying to do it is I don't like using these numbers in it, because these numbers are cleaner numbers. All right. And a lot of times your answer ends up just being putting that on there. So if you're dealing with anything from kilo to milli, you can just move the decimal places like you're used to doing if you understand that. All right. But if you're using anything outside, remember that in this course, I'm adding giga and mega and micro and nano, and they're going to be extreme cases. They're going to be further out. So just kind of keep that in mind. All right. So kind of moving forward notes wise, I will give you a copy of that chart so that you can use while we're practicing it, but eventually you have to get that cycle memorized. So I would just memorize the prefix, the abbreviation for it, and the exponent factor. That's how I would do it because it makes life easy. And there's a way to kind of cheat on it. If for memorization, I'll show you all that another day. All right. So one of the things, not really cheat, just a quick memorization tactic that I've learned. All right. So volume is a derived unit. What that means is we have to use a calculation to get there. So when we talk about derived units, when we talk about volume as a derived unit, volume is a product of length times width times height. All right. And so that gives us, and when I'm talking about this, I'm talking about a regular shaped object, something that we can measure length, width, and height on. So volume is a product of length times width times height. If it's a liquid volume, then we can measure it directly with a graduated cylinder, something like that. So when we're talking about units of volume, if we do something like length times width times height, hopefully when you measured them, if you measured length in centimeters, you also measured your width in centimeters, and you measured your height in centimeters. So that means that 1 unit of volume will be something like centimeters cubed. You could also have meters cubed. You could have inches cubed, just depending on whatever you measured it in. So units of volume are going to be things like cubic centimeters, cubic millimeters, cubic meters, things like that. Now, we have a direct conversion because water is kind of our basis for comparison of everything. We set the density of water to 1 gram per cubic centimeter, but it's also 1 gram per milliliter. So we have a direct conversion that says that 1 milliliter is equal to 1 centimeter cubed, or 1 cubic centimeter. Sometimes you'll see centimeters cubed abbreviated as cc. That's the same thing. Now, why this is important. When we deal with density problems, frequently we're going to have to go, sometimes your answer might be in grams per milliliter when you're using cubic centimeters. You can know that a cubic centimeter and a milliliter are the same thing. They directly convert. Sometimes some of the questions that you're going to see in active will be like that you have it's just a random thing. It's not really a science thing. But just say that you have a car engine that's a 454 cubic inches. How much is that in liters? And so you have to go from cubic inches to cubic centimeters to milliliters to liters. All right. And so that's where you would use that. And tomorrow I'm going to kind of teach that. It's not a difficult thing. It's just more kind of thinking about it and going into it. So it's a derived unit. Derived unit means that you have to calculate it. All right, it means you have to do some kind of formula to get there. You have to multiply, divide, add, subtract, whatever to get there. A lot of times with derived units, you have compound units. So density is another derived unit. So remember that density equals mass over volume. So for density, you get units like grams per milliliter per centimeter cubed, grams per inches cubed, grams per feet cubed, grams per meter cubed, things like that. All right. Does everybody have what they need off of this one? All right. So whenever it comes to the word problems and all that we're going to get in this class, there's going to be there's going to be tons of word problems in here. All right. There's not going to ever be, well, most of the time there won't be just a formula that you can plug the numbers in. So you're going to have to reason out what you can do. So you'll take it one step at a time to get to the answer. So when we're looking at these, don't worry about copying all of this. This is just talking points for me. Most of the questions that we do in this class are going to be unit conversion type questions, where we're going from one known unit to another known unit through a conversion. Just like I showed you before between metric, that works for English metric as well. In your periodic table reference packet, I have a couple of basic ones like inches to centimeters. I have, gallons to liters or something like that. And so you should be able to get from any one imperial unit to a certain metric unit just by a couple of steps. And there's no like direct formula for it. You just have to know the conversion factor and be able to apply it. So again, there won't necessarily be a direct conversion factor or a direct equation to plug it in. You have to kind of reason it out. Now, I do want you to write some of this. All right. So we use dimensional analysis in this class. I kind of already started establishing what dimensional analysis is. In dimensional analysis, we are going to multiply and divide units to cancel them out, just like you would with any other algebraic quantity. The kind of key thing in this one is in dimensional analysis, you must always include the units in your work when you're showing. So another way that you'll hear me say that no naked numbers. All right. So, for example, this might be a number that you know off your head, but what does 365 days relate to? 1 year. All right. So we know that that is equivalent to a year. What about 24 hours is 1 day. And then what about, so 1 hour is 60 minutes. And one minute is, all right. So if I said that I've been teaching 22.7 years, and I wanted to know how many seconds I've spent teaching, how would I start this process?
So you tell me days of 365 days times 24 hours.
All right. So in dimensional analysis, I need to get rid of, go step by step, right? So I'm starting in years, so I'm going to put years down here. So for every 1 year, 365 days. I can get rid of days. 1 day is 24 hours. I can get rid of hours. For every 1 hour is 60 minutes. And then I can get rid of minutes and go to seconds. For every 1 minute is 60 seconds. So if I wanted to know how many seconds I've been teaching, I do 22.7 times 365 times 24 times 60 times 60. Now, that's not really a calculation that you ever would just intentionally do, unless you're writing that song for Rent, where they count the seconds in a year or something like that. Yeah, that one. I don't ever remember the number, but I remember the song. All right, so that's and the reason why we do it like this is we're trying not to let our units get away from each other. If you remember the video I showed from Crash Course, like early on in this, and he was saying, don't let your units disappear, or don't let your units trick you. That's the things that they're trying to do. They're trying to trick you. And so as long as you know your conversion factors, I can flip any of those conversion factors either way in this calculation, depending on what I'm trying to do. So what setting it up allows me to do, if I'm in years and I divide by years, that means years goes away. If I'm in days and I divide by days, days goes away. If I'm in hours, hours goes away. If I'm in minutes, minutes goes away. Same thing works with like miles per hour. If I need to go from miles per hour to meters per second, I can do that. I would change the miles to meters first, and then I would change the hours to seconds next. And I can do that by putting it on top or bottom. All right. So most of the time in the prompt, we're given certain quantities. So if I said that I'm going 65 miles per hour, and I want to know how fast that is in kilometers per second, where would I start? Well, let me ask this. Is there another way that I can write miles per hour to make it more reasonable to use as looking at the units? So I can write this as 65 miles for every 1 hour. So if I'm going 65 miles per hour, I can travel 65 miles in 1 hour. All right. I need to get to kilometers per second. So does anybody know? Let's try to get from miles to kilometers first. Does anybody know a conversion factor from miles to kilometers? Not 1,000. So I want to get rid of miles. I want to go to kilometers. And I know that a mile is a little bit bigger than a kilometer. So I think it's like 1.602 miles for every, for every 1 mile, it's 1.602 kilometers, because a 5K is about 2.5 miles. All right. So I would do that. That gets rid of miles. And then now I'm in kilometers, and now I can work on getting hours to second. So I put hours on the top. For every 1 hour is 60 minutes. And then for every one minute is 60 seconds. And I would do it like that to solve.